So my name is Johan Eker. I'm a principal researcher at ERICSSON. I've been at ERICSSON for 13 years now. I started making cell phone software. We made the first Linux port. We did Linux and Java. And at a point in time that people said that no one would ever run Linux and Java on a cell phone. So that was killed, and that earned me a PhD, and I told you so. After that, I worked with Daniel, for example, in programming multi-core software for base stations. And since 3 years back, I'm working with cloud. And at ERICSSON, I run the ERICSSON Research Data Center, which you see here. That's one of my 3 main tasks. And in addition, I do mission-critical cloud and Internet of Things. And my main interests is in the area of programming. I'm a software guy, and I'm a lazy software guy, so I want my programming to be simple. So this talk will be a strict subset of previous speakers' presentation, but I will zoom in on how can we make this simple to program, not only that we can program it. So I will basically tell the same story as the previous speakers have done today, so please bear with me. So yeah, and I'm a researcher. I have to do the same disclaimer as Giovanni did this morning, saying this is research, so if you want to buy it, you might have to wait. And it's not necessarily the opinions of ERICSSON either. So ERICSSON Research is a fairly large research organization. We are 650 people worldwide. It's like a university. We have 50% are PhDs. It's like a university without having to apply for money and write reports, and instead we do research. We're spanning over from US to India, China, and Europe. And we're divided into 8 divisions. You can think of them as departments. Well, you have radio people, we have wireless people, we have sustainability, and I'm in the part that's called cloud technology. And we're roughly 60, 70 people who do this. When I show this picture, sometimes it's like an IQ test. What is the next symbol here? So working in telecom is sort of it's a path. After 4G comes 5G. So we started in ERICSSON with 1G. That was the analog systems. That was ending in the late 80s. Took over by GSM. We had 3G coming in around the millennium, 2003, we made the first platforms for that. And with 3G, you had connectivity. You could send data traffic. With 4G, we had some proper broadband connectivity. And with 5G, we get what we call at ERICSSON the network society, with everything that actually can and benefit from being connected will be connected. And likely the things that do not benefit from being connected will also be connected, like everything. And that's where the trillions come from. But we don't think trillions yet, but we hope for trillions. So what is 5G then? We heard that it's everything under the sun, that is sexy. I don't know what your preferences are, but at least we have bandwidth. With 3G, we had bandwidth around half a megabit per second. With 4G, we go to 40 to 100 megabits per second. And with 5G, we're going to bit rates that are above 10 gigabits per second, up to 25 gigabits per second. And we have radio and transceivers in the lab in Kista. We've been demonstrating it, bit rates up to 5, 10 gigabits. And the reason why we can do that is you go for MIMO, you have multiple antennas, simply, and you have what's called beamforming. So instead of broadcasting to everybody, you're broadcasting to a certain terminal. Thereby, you can reach much higher efficiency. And if you want details, I think Daniel is the guy to do. I direct all the 5G questions to Daniel. Sorry for that. We got network latency under 1 millisecond, which would then require, that you have to do some drastic changes to the radio interface to manage to get 1 sub-millisecond latencies. Capacity expansion by a factor of 1,000. But maybe the most interesting thing here is for IoT is energy efficiency gains by a factor of 1,000 per transported bit, meaning that we are now with 5G not only directing the attention to terminals where people can phone and communicate, to stream video and so on, but also to be the basis for the next IoT evolution that comes. So this sort of sums up the 5G. It should be added that 5G is still in the early standardization phase. So exactly what choices will be made remains to be seen. So when I say 5G in the talk later on, it will mean, something that captures those characteristics, but not necessarily being implemented in 5G network. So just like we heard previously about NFV, I mean, all the operators and all other enterprises have made huge savings going from having the IT equipment in real servers moving to the cloud. Well, we all know that. Cloud is not a technology area. Cloud is a way to save money. It's just a business proposition. And of course, they want to do the same savings, not only on their IT equipment, but also on their network equipment. So 3 years ago, roughly, they started this initiative called NFV, Network Functions Virtualization, where you aim to replace, just like we heard, those black boxes, which are the firewalls, the deep packet inspections, etc., running those as VMs on top of commodity hardware. So basically, what this means that now Ericsson will not only sell a box where everything is pre-integrated, we'll sell the virtual machine or the hardware or both, which is a huge shift for the industry. And there's an interesting open source project called OPNFV, where Ericsson is heavily involved, where we do standardize the platform, the infrastructure that runs on this, and also the NFV components. So we heard about trillions of devices in the previous talk. I think I'm going to settle with 28 billions. That's the exact number we have. This is from the Ericsson Mobility Report. So the predicted number of connected devices will be 28 billion by beginning of the next decade. And you can see here, so the orange in the bottom are the cell phones. We're going to move from 7.1 to 8.7. It's not a huge increase. So the largest increase is from machine to machine on the top, where we have non-cellular and cellular making quite a huge increase. And we expect that increase to be much sharper once 5G is fully deployed. And interesting to note here is mobile phones will be 8.7 subscription plus laptops 2.8. Given that we are like 7.5 billion people in the world, it means that quite a few of us are sort of doubly connected, which is of course a good thing, I think, that you should all be doubly connected. So, and we get more. We get more of those devices, and sensors are becoming increasingly cheaper. So you can take those trackers for that you can do when you train. Go for $200 a pop, and then you summarize sort of what are the ingredients in here. Basically, you can get a Wi-Fi connected gyroscope accelerometer. It all sums up to a couple of bucks, which sort of shows that not only can we get more of those devices, but sensors are becoming increasingly cheap and sort of sustain the idea that we could have a very sharp explosion of IoT sensors and devices. And in this setup here, the cost $200 is more for the programming and putting it together and marketing than it's actually building it. And in Giovanni's slide this morning, you spoke about, in the beginning, cloud was about saving cost. That was basically moving the service to somebody else, but going from being an infrastructure as a service, we're moving into having intelligence as a service. We are not having just virtual machines that are set up, but also we have deep learning algorithms, you have machine learning, natural language processing being a service that can be sold, in the format of the cloud. And this picture here is from Kurzweil. He predicts that we'll have a human brain in 2030 we can actually be able to simulate a full human brain in a little more than 10 years from now. I don't know if that's true, but it's a prediction. It's easy to make predictions, of course. And yesterday I learned that we have heard previously that Alpha from Google were possible to beat a professional Go player in China. And yesterday I learned that there was an AA machine that played football and was actually able to beat some students in Canada. So we are making progress every day in providing very much smarter cloud. And in parallel with this much smarter cloud, we also get a much more flexible infrastructure. This is a disaggregated server, where instead of buying servers that are pre-integrated with hardware, disk, everything comes in a rack, which is fairly inflexible. What we see in the next generation here is servers where you put CPU, RAM, network interfaces, and disk on sleighs, and you can configure them dynamically. And you do that via a software interface. And we have a product called HDS 8000. It's out now, where we actually can configure the server dynamically. And then you combine that with software-defined network, just like we heard in the previous talk here, and you get software-defined infrastructure, which then makes everything from the ground up very, very programmable, which opens up for lots of interesting research challenges and opportunities, because now we can have so many buttons and parameters that we can change dynamically. So you get it. We get more of the things we like, and we get less of the things we don't like. Everything gets better. So what do we want to use this for? Well, what we basically get now is a very, very big computer. You can program everything from the sensors at the edge, closest to the left here you have sensors. You can program the base station. You can program the nodes in the core network. Remember, they would become virtualized, meaning they actually, we could place computations, virtual machine there. We have data centers that are internal, that are the central offices for the teleoperators. And then we have the cloud to the right. And in this picture here, you can say that the latency will increase when you go to the right, but price will decrease when you go to the right, because it's cheaper. The plain vanilla cloud is just about price. So you get the cloud with, maybe with SLAs that are maybe not 5 nines, but a few nines, but it's very, very inexpensive. But then you move to the left, you get some more nines, but you have to pay more for it. You get lower latency and so on. So there is a very simple, or at first glance at least, very simple trade-off between money, location, latency, availability, etc., which is, of course, a very interesting research problem that we just heard a few solutions to. So application areas that we are looking at Ericsson is ranging from mining to e-health to transport. We have, for example, this collaboration integrated transport lab with KTH and Access. We have surveillance, etc. we're working with. And you take a look at a scenario like this, public safety as a service. So what is public safety? Public safety can be anything from the coordinating police or fire, there was a wildfire in Sweden 2 years ago, and there was a really big problem in coordinating the efforts to putting it out. Typically, the public safety systems today are run on a very local basis. So each of the communes, they have their own setup of public safety. So now we're thinking of what is public safety as a service? Can we sort of rent and scale capacity? Because when things happen, you really would like to have a very flexible and very system with very high resilience to failure and very high availability. And when you think of surveillance, is it really, in a city with lots of cameras that are good and lots of sensors, wouldn't we want it to be the case that when something happens, we would like to use all the sensors in the city? So if you think of a city like Linköping, for example, then they have sensors from the energy department or for the environmental department, have the sensors for monitoring the CO2 level in the city. And then you have the traffic department that actually also have the same sensors. And then you have another department that has a similar set of sensors. And then you have some department have the cameras and other have the cameras. So if you think of the city as one big computational platform, it's one big computer instead, and where we can share the sensors. So once I need the sensors, like the camera or the CO2 monitor, I will not have to put them there myself, but I will be able to share sensors in the same way as I share computational resources in the cloud. I mean, cloud is about its economy. The more we can use our sensors, the more we can share them, the less the cost. So what if we could build a system where when I need to have video streams, I can just hook myself into those video streams and rent video from them, or use other kind of sensors in the city. Another thing that we did last year was at the Barcelona Mobile World Congress, we had this excavator that was located in somewhere in Sweden. I don't remember where. And it was remotely controlled from Barcelona. So there was this guy with the Oculus Rift, and he was working with the excavator remotely. And we could figure out that the delay was roughly a couple of hundred milliseconds, which was on par with the delay in the dynamics from the excavator itself, which made it sort of possible for a skilled controller to actually, to work with this remote excavator. However, there was no feedback. So if we then think of what we would like to add feedback, so I'm moving my excavator, or I'm having remote brain surgery, then I would like to be able to get some tactile feedback, so I can feel that I'm hitting something, in particular if this is remote brain surgery. And of course, you don't want to have a remote brain surgery, but if there is no other way. So this is stuff that I did with a student at the control department, where we actually had a haptic six-dimensional handle with haptic feedback. We were connecting it to the cloud over wireless 4G dongles. Then we had an AV robot with force sensors, and we did experiments. And it turns out that around, if we had delays in the network that were much more than milliseconds, that turned out to be lots of problems. Really hard to make good use of the feedback, unless you did some smart. So I guess there are two issues here for the control guys to figure out how you can handle the variations in the delay and the longer delays for tactile feedback, but also for us to actually come up with 5G and make sure that we have 1 millisecond latencies. I think that is a case for where 1 millisecond feedback actually, 1 millisecond latency actually is a very useful thing to have. Another thing that we are working on is SKF. We are building a 5G factory, basically controlling and configuring the factory from the cloud. And the use here for, if you have a factory here, we are focusing on availability. It's here we don't necessarily need sub-millisecond latency, but we need lots and lots of sensors, and we'd like to control it from a central point, and we would like to be sure that it's available. If the factory goes down for a longer period of time, it's very, very expensive. So availability and latency are key things. And already now we have, this should be an animation, but no. Already now we have an installation in Krankberg mine. It's a mine that is operated by Boliden, a Swedish company. And as of March 31, they actually launched a system. It's not, they call it the 5G mine, but it's actually just 4G. And but I guess that's the name of the project. They have 300 kilometers of mine that has been equipped with radio equipment, and they do autopilot of vehicles inside the mine. They do remote control wheel loaders and stuff, and they, of course, use it for standard communication. And one of the things here that are highlighted is the use of standard equipment for communication. Previously, in the mine, you had to have special phones, special ways of communicating. So, for example, when emergency personnel came to the place, to have to exchange their cell phones for other cell phones going into the mine. So just having the possibility to use standard equipment is a big thing compared to I mean, it is possible to build this without 4G, but with 4G you get not only you get convenience and the use of standard equipment, and in addition you get a decent latency. With the 4G network, you have according to our experiments, you have 30 to 40 millisecond round trip, which is okay for quite a few control applications. So now I've said we know that IoT is the future, and it's going to be great, right? So, but you know, there's some things that we have to solve first, because I think that it's not enough that the technology is in place. We have seen this before, right? It was in 2001. We had this ERICSSON Electrolux screen fridge where you have the milk telling you that it was, you know, sour. So you could, and you could see that without actually opening the fridge. And I mean, in that vision you had, you know, the future was actually a house with lots of screens. So, and I think that would you know, so it's not enough that the technology is in place, and it wasn't in place then. But even if it's in place now, it's not a done deal, I would say. You see to the right, you see the ERICSSON iPad, or that's sometimes what we refer to it. It's like the iPad without the iPad experience, or the apps. but we were. So previously, what failed last time? Well, no digital experience, neither from the users nor from the providers. No apps. At that point in time, even for cell phones, there was no app market. So there was no way for people to actually add their own functionality. And of course, technology was the performance. The performance in communication, the performance in battery power, the performance in sensors were not as good as we needed to be. So are we good now? Will it happen now? Will IoT actually explode? Well, this is a slide that I stole from Boliden. This is how they think of things. You know, the Atlas Copco products are connected to. So everybody that is working on this market now have sort of silos. It's possible to address certain use cases. It's possible for one provider to connect to their own stuff, right? And it's possible it's possible to build those applications, but it's really hard to reuse code. It's really hard to have some interoperability between devices or applications. So what can we do about that? Oh, here's another thing. From the World Economic Forum last year or 2 years ago, you know, what are the perceived barriers to, you know, for industrial internet to happen? Is a lack of interoperability and security concerns. And I think the security concerns are maybe the tougher one. Because if I have my mind being remotely operated, you know, I can think of many bad things that could happen. So you really would like to have a security framework that is as, well, you want that to be in place before something happens. So security and interoperability. So what is the state right now when we go to IoT? Well, there are plenty of devices, as I said. It's super fragmented, it's specialized. We have plenty of APIs, and they're connected, yes. Do they talk to each other? No. When we have this client-server model, it's basically you have clients, which are sensors, and they will report up to the cloud, and they will store data in the cloud, and then they will report back. So it's basically, you know, we're still in a client-server model. And if we're going to take advantage of edge cloud and the low latency, we need to get away from this simple client-server model. And unclear business model, how are you going to make money? We're entering into data economy. If I have put up lots of cameras and sensors, and I own those sensors. I would like to sell that data. So it's not about me having this camera. It's about me selling footage to somebody else who would like to buy pictures of the city in a certain time when something is happening. So the business models are still very unclear. So do we lack standards? Well, if you go from 2009 to 2015, you can see there is quite increase in standards. 2009 there were few, now we have lots, and those solve very specific and very pertinent problems, of course. But so I'm a lazy guy, so I want to be simple to program. That's my idea. I want it to be. I want to write those applications that connect the end nodes and the cloud and everything in between. I want that to be simple. So I can write it. I'm going to write a tool, so I can write it. That's my goal. So here are those. The guy to the left here, he's fed up with writing REST APIs and connecting containers and deploying things manually, and he's so bored. We want to have something that is simpler. So in this project that we are working on now, basically could be characterized with those 4 bullets underneath. We need to lower barriers to entry. In my view, I would like to have a small company from some incubator being able to write an application that integrates cloud services, IoT devices, and everything in between, being able to sell that application on a market to an operator that operates it, do lifecycle management, and I want it to be, what can we make it possible for a small company to do that on top of Ericsson equipment and utilizing IBM, services in the net. Can we? But I want you should not need to be Ericsson or IBM in order to build that application. It should be possible for someone much smaller, because I think that's where the creativity comes. You can think of cell phones. In the beginning, when I was working with cell phones, when we make applications, we actually, it was 10 guys going into a room, and we figured out what is the next killer application, and then somebody come up with, we can have a, poker game. And then you open up with the SDK, and out comes Angry Birds. It's not like 5 guys at Ericsson would conceive Angry Birds or Goat Simulator or something. It's just we need to provide an SDK so people who can innovate and are creative can create, and I can do the SDK. I think that's code reuse and portability. We need to be able to take the mining application and the public safety application and reuse components between them. We need to start sharing. Sharing is caring. We need to make sure that all the sensors that we put out there should be possible to reuse between applications and between users in a cloud-like fashion. And we need to create a marketplace where we can actually charge for it. So if I put a sensor here and I will rent it to somebody else, I would like to be able to charge for it. And I would like to be able to charge for components that I develop. And maybe I would like to charge for them for reusage. Every time somebody uses my virtual sensor, I would like to charge them, just a tiny bit. Some way of getting a market into there. And of course, security needs to be in place from start. If I'm thinking of actually sharing cameras, it goes without saying that you have to be certain that the data streams that comes from the camera is the correct one, and that the one who's using the data stream is the one who we think it is. I think we all can agree on that. But I think that security should be something that we build from ground up. And of course, if we don't think it's going to be 28 or maybe trillion of devices, it goes up like that, we need to figure out how to manage this. Have all those applications that are running all over, all the edge nodes and everything in between. Should we have a central resource manager, or should we have a distributed way of having them self-organized, for example, or should we, I would vote for something decentralized, self-organizing. And then lifecycle management, which is, we need to be able to upgrade, maintain, maybe remove applications. If you make, so we need to have a way of taking an application and giving it to an operator like Telia, for example. I would like Telia to operate my mining application. How would that work? How would I deliver that application to Telia, and how would I know how to operate it? There needs to be a clear interface for how I will hand over that application, and to upgrade it, and to make sure that it's actually alive and cooking. We heard previously today that containers have some advantage over VMs in terms of understanding how to execute, but maybe we could go further than containers in knowing what works and not works. So here we go again, this picture. When everything is being programmable, then the world becomes a very big distributed computer. Basically, you can program everything. The question is just how. So, and from now on, this is what we do. We call it Calvin. It's your new best friend in IoT. I would not claim to say that this is a solution. I'm just saying that this is what we are actually working on right now, the ERICSSON research. It was demonstrated in Barcelona for a few months ago. Calvin is the internal name that we use at the ERICSSON research. Basically, we tried to figure out how we can abstractly describe an application. We can connect components. We can have a separate way of deploying and managing this application. If you want to know more, there's an URL, and it's all open source. And we have a team of 5-6 people who are working full-time on this for 2 years now. So it's not huge, but it's a sizable group. You don't need to be more than 5 to make some good software. And we're focusing on the developer experience. We are using containers and everything there is, but we are starting from the point of, if I'm a two-man band and I want to write this application, what would I need just to make it really simple, and I can hand it over to an operator. So basically, we describe an application as a data flow graph using an actor model. And for those of you who have worked with me previously, it's the same thing that I've always been doing for 15 years. So it's actor models, so then it's the data flow programming. And but basically, we have an abstract view of how an application works. So an application is described as a graph with the actors, and those in turn can be arbitrarily complex. And what we are working on is issues like that. You have an application that is, it's like a graph of sort. This is just a pipeline, but you can imagine an arbitrary complex graph. The idea is to deploy that graph onto this huge infrastructure. You can think of this as being self-managing, so it will just spread itself out. And how would it spread itself out? Well, in our case, by timing constraint. We have requirements. We need to have end-to-end latency. We need to have a cost down. So you will minimize the cost while maintaining the latency from end to end. And you do that in a distributed fashion. Figure out how should I move around this graph. And at the same time, we don't only have one of those graphs. One application and one hardware. That's kind of boring. So instead, we have many applications at the same time. In this case, you have those cars, for example, could be having an application. I have a car application where I say that every car I meet, I would like to have a report on the road conditions. So if I'm driving in the winter and I meet a car, I just would like to have the report from that car saying what are the road conditions because the likelihood is that the guy that comes in the car just was where I'm going to go. So I would like to have that information. So I would actually pay for that information, some way. Maybe by exchanging data, he gives the same data from me, but somehow I would like to, So I will define my application with a geospatial. All the cars that I meet, I will take the data from them. It could be, but in the same time, might not only be me who get the same data from that car. So that's how we think of an application. And when it comes to mobile networks, of course, mobility is always an interesting or a necessary part. So the bus that goes there is connected to the base station that is closest because you would like to have low latency. However, when I move, I will go from one base station to another base station. So we would like to have, handover of not only of the data connectivity, but also with the code. So super fast migration, which means that moving VMs around base stations is not what we want to do. Moving containers around base stations, nah, not either. I mean, containers are not that good for migration. So we'd like to have a program model that allows us to move code. Maybe, stateless Lambda functions could be one way of skinning this cat. But that's where we're, stateless is good for this, or a state that is actually possible to migrate quickly. So that sort of summarizes my talk. We are working on this Calvin project. We are super interested in resource management and adaptivity. We'd use two autonomous systems closing the loop, where we use real-time analytics to manage the systems. We need real-time analytics and all those things to run on top of the system, but we also need something to figure out how to, for example, move nodes around, figure out what is the solution for placing nodes such that we have latency constraints fulfilled, et cetera, et cetera. Security, that's a big deal of what we do. Figuring out how can I trust code and how can code trust hardware. Figuring out business models. How can I sell my code in a completely automated fashion? Maybe using, we're looking into distributed ledgers right now for understanding if that could help us. And then, my pet interest is in the software architecture and languages. How can I express an application? What is an application? In the model, we have a client server. It's fairly easy to understand what an application is. But when I have a graph like that, what is actually an IoT application in this sense? So with that, I will conclude my presentation. Oh, not. Well, we just skipped that. I had some equations. That was Mikael. I was just want to impress him with some equations, but I skipped them. So we're just working on the details. So with that, I will take questions, and I can take the time to recommend this book, From Machine to Machine to the Internet of Things, from my colleague, Jon Höller, whom I've stolen some slides from also. So those are the people who are contributed to this presentation. So thank you.